Let's dive into something tiny. We're talking about one of the biggest challenges in all of science. How in the world do you measure something you can barely even see? This question is going to take us deep into the microscopic realm, a place where the tiniest mistake can have absolutely massive consequences. I mean, really, think about this for a second. We're talking about amounts of liquid so small, they're almost impossible to picture. You know, a single teardrop, that's about 50 microliters. We're about to discuss measuring things that are 50 times smaller than that. So, yeah, how on earth do you do that accurately? Well, the answer comes from this little guy, the micropipette. This thing is the unsung hero, the real workhorse of pretty much every modern lab you can think of. Genetics, chemistry, you name it. Its job, to move incredibly tiny amounts of liquid with precision. But precision is a tricky word, isn't it? Because, let's be real, no tool is ever perfect. Yeah, that's right. Every single one of these super high-tech tools has a small, built-in inaccuracy. Now, this isn't a flaw or a defect. It's just a known part of the physics of how it works. It's called the micropipette PE for short. And honestly, understanding this little error is what separates real, rigorous science from just guessing. Okay, so that leads to the big question, right? How much is a little bit off? And here's the fascinating part. It's not just some random, unpredictable wobble. This error is actually predictable, and it changes based on how much liquid you're measuring. Let's dive in and look at the actual numbers. All right, so this table breaks it all down for us. You can see we've got different micropipettes for small, medium, and large volumes. But I want you to focus your eyes on that middle column, the one that says typical error percent. Watch what happens to that percentage as the volume on the left goes up. There's something really interesting, kind of counterintuitive, hiding in plain sight here. So, did you see it? It's probably the exact opposite of what you were thinking. It's an inverse relationship. The smaller the volume you're trying to measure, the bigger the potential percentage error gets. I mean, how wild is that? The stakes actually get higher the smaller you go. So for those teeny tiny volumes, we're looking at an error of up to plus or minus 3%. Now, I know 3% sounds like nothing, right? But when you're working at the scale, trust me, that's a huge deal. Then you move up to the medium-sized volumes and boom, the error drops. Now we're down to about 1%. You can already see the precision getting better. And finally, when you get to the largest volumes these tools handle, that error shrinks all the way down to just 0.5%. That is an incredibly tight, incredibly precise tolerance. Oh, wait a second. If every single one of these measurements has a built-in error, how does science even anyone trust their results if their most fundamental tool is sort of flawed? Well, here's the thing. Don't ignore it. They manage it, and they manage it through this really strict, disciplined process. We're talking regular calibration, where they're constantly checking and resetting the pipette's accuracy. We're talking proper maintenance to make the moving parts are working just right. And believe it or not, just careful handling by the scientists. Because yeah, you hold the thing can throw off a measurement. This isn't some free-for-all where every lab makes up its own rules. No way. These practices are all laid out in global standards. Like ISO 8. What that is, it ensures that an lab in, say, is totally comparable to one done in Toronto. It's like a shared global language of precision. So, let's zoom out a bit. Why does this matter so much? Really not about this obsession with error. It isn't a chase for a flawless measurement. It's something way, way deeper. And is the key takeaway for this whole thing? Science isn't about having perfect tools and pretending they're false. It's the complete opposite. Real scientific rigor is about rigorously understanding and accounting for those flaws. Error, it's not a failure. It's just a variable you have to plug into your calculations. And believe me, the stakes are as high as that tiny 1% error we were looking at. It might sound like nothing, but in fields like molecular biology, developing new medicines, that tiny fraction can literally be the difference between a massive breakthrough and a dead end. So, I'll just leave you with this thought. If this is the incredible amounts of care, attention to detail that goes into measuring one little drop, just try to imagine the kind of rigor that supports the entire foundation of science. That very commitment to understanding action, that ironically lets us get closer and closer to the truth.